Hello, everyone. Good afternoon, and welcome to the QBN Quantum Leadership Session. Actually, today is the session 4. We are addressing quantum computing, and for us, it's a pleasure to having these top speakers with us. I'm going to present them in a few seconds, but please let me thank you for being here with us, for your time and yeah, all the experiences that you are going to bring to us. Just a little bit about the introduction of these sessions. So these leadership sessions, we started them a few years ago, actually. They were very successful. Hundreds of views and they were like very interesting for everyone. But we did it at the European level, right? And right now, QBN is growing at a global scale. We have more than 80 members nowadays, and we have members from the US, from Japan. So we thought that we could bring this format internationally. So we would like to provide to all startups, corporates, and research institutions to share their visions, solutions, success stories, and collaborative efforts, and showcasing their leadership positions. In a nutshell, the end goal of this format is to involve every leader of each sector, whether it is using quantum technologies as an end user or from different industries, or developing quantum technologies. So that we can create a strong quantum industry together. I like to say through an African proverb that if you want to go fast, go alone. If you want to go far, go together. So that's our philosophy of from QBN. So I'm presenting the top speakers of today. So we have Alicia Wilms. She's quantum computing scientist at Porsche Digital. Then we have Michael Brett. He's a worldwide business development and go-to-market strategy lead in quantum computing for Amazon Web Services. He's joining us from the US. Then we have Adrian Vetter. He's head of software at Plan QC and now a QBN member very recently. So welcome again. And last but not least, Nikolai Maul. He's quantum computing scientist at the big pharma Boehringer Ingelheim. So for those, hi Nikolai, welcome. So for those that are joining recently, you will have the chance to participate in the Q&A section by the end of the meeting. Just type your questions on the Q&A chat on Zoom, and then by the end of the session we will revise it and we will have an interactive discussion. So for those that don't know about QBN, we are the world's leading networking company organization that we promote business creation. We promote the development of organizations, and we provide all the activities and all the support in order to foster the sector of the quantum technologies and its value chains. So as you see in the picture, we bring together all the key players of the sector, from universities, startups, to large companies, investors, research institutions, and politics. So we do it through 5 pillars. We provide the perfect platform online, so members can interact with each other and find opportunities. I will explain it a little bit later. So what's inside this platform. Also, we provide meetings in a presential mode. Last day we were in the Barcelona Supercomputing Center. Also, I'm going to show a little bit about that. Sorry. Also, we we support our members with marketing and public relations support. We also work with governments to foster better policies for the sector, and we help our members with business acceleration and other consulting services. So we are already more than 70 members, approaching 80. I need to count it, but yeah, between 70 and 80, we are growing so fast that we lose track of the exact number of members, and we are very happy to have them as supporters of this big network. As I mentioned before, we have this QBN portal that help every member to connect with each other, to provide job opportunities, access to call to fundings, and yeah, access to news and events of the industry. And also, they have members have exclusive access to different meetings and access to presentations and the attendee list and access to working groups. Some more news from the network. We recently developed a position paper because Germany published a new strategy of 3 billion euros to invest in quantum technologies. So QBN gathered all the members and created a position paper in order to discuss this strategy, and yeah, we ended up with the conclusions that this action plan did not meet some challenges. Some goals were kind of vague and not precise. So QBN is giving recommendations to the ministry in Germany about the quantum technologies and also other different aspects from the organizational to the structural level, like funding and all the policies for startups and so on. So yes, we are going to publish this position paper very, very soon, and we are going to send it to the German ministries and the European Commission. But this is also thanks for the members that are supporting these initiatives. And on the other hand, also some good news. We did a QBN meeting on quantum computing and applications at the Barcelona Supercomputing Center. It was a full 2 day of a lot of keynotes, the visit to the best, the most powerful computer in Spain, which is inside of a church, very particular. And we have different networking dinners and lunch dinners. So it was a day full of experiences. We also had presentations about quantum computing in many industries like energy, finance, chemistry. And also we created the working group on quantum computing and applications. So also this is a super benefit for QBN members. So you can, if you are inside, you can make an influence for the industry, right? You can, as Steve Jobs said, you can make a change in the world and make an influence. So that's what we provide. Some more events upcoming. So full of events at World of Quantum by the end of this month. We are going to have a workshop on quantum communication. We're having a VIP barbecue in a rooftop in Munich. So if you have not reach out if you want a special invitation. We have a networking lunch with pitches at in collaboration with Quantum Delta Netherlands, and we are also organizing 2 QBN meetings, one in quantum computing, photonics, and also then in quantum sensors. And last but not least, we are also in the pavilion. Sorry. So we have a stand in the exhibition where we gather all our members and we share the space as a team, right? And this is the key event of this year. This is the QBN Quantum Industry Summit. It's the International Quantum Business and Innovation Conference taking place on the 10th and 11th of October in Stuttgart, Germany. And I'm very happy to promote this because this is very different as we've seen until now. So normally we see many events on quantum technologies, maybe for one single technology, or maybe we can find something about business. But here we bring everything together. We bring business, politics, what's going on the investment and entrepreneurial sector in track 1. And in parallel, we will have the track 2 that is about quantum technologies and supply chains. Here we will find all technologies from quantum computing to quantum communication to photonics to enabling technologies, everything. And in the third track, we will find how quantum technologies can be applied to every industry. So we will have companies showcasing their services and products in their own industry, pharma and biotech, energy, finance, material science, medical technologies. We will have everything there. So I invite you to check it out. But also in the agenda, we will find networking opportunities. We will have one-to-one business and investor meetings. And we'll have also a very private investment forum for startups to pitch in front of selected investors, and live demos for software companies, but maybe also for hardware. And yeah, I want to shout out our current sponsors. We have gold sponsor Cruise, and also the bronze sponsor HQS Quantum Simulations, and also more members are joining us in the upcoming days to become sponsors. And also we have other co-exhibitors, Squeaks, Diatop, and Econotics in our booth. And very interesting for attendees is that we will have featured speakers from the European Commission, like Gustav Kalb. He's the acting director on digital excellence and scientific infrastructures, and in the European Commission, as I said. And for example, Neil Abrouk, he's the head of the French National Quantum Strategy at the government of France, or Olivier Tonneau, he's VC partner at Quantonation, another VCs joining us, or from the other side of the wall, a policymaker from the Department of Commerce in Maryland, in the US. So as you see, this is a big conference. Hopefully we will have more than 500 participants, and we will have more than 50 speakers across these 3 parallel tracks. So I invite you to check this out. The website is going to be available by tomorrow, and you can become a sponsor. So I invite you, to check it out, because it's a super opportunity for, increase your visibility, shape the agenda, make an influence, and make a strong quantum industry together. So that's all from my side. If you want to become a member of the QBN, please reach out. You will have many other opportunities, as I said, to share your job opportunities, exchange in the QBN meetings, and be at the cusp of the industry. So yes, that's from my side. Now I leave the floor to Alicia Wilms. She's a quantum computing scientist at Porsche Digital, and so I will stop my screen, and you can share yours. Thank you.
Thank you very much, Adria. I hope everybody can see my screen from now on. So I will talk about how to approach quantum computing as a company. And what we will talk about is mainly based on our book chapter from a book I recently published together with Florian Neukart, with trying to evaluate that we as Porsche Digital, like as a digital subunit from the Porsche AG, our goal is to create quantum value. So we want to create value with quantum technology, whatever this might mean and be. Let's discuss this later. And how to do this in such a big corporate is what you will learn about in this presentation, or what I will talk about, mainly focusing on the main challenges of integrating quantum technology, and on the other side, what could be a reference path for integrating quantum technology inside your company. And along these challenges that you encounter in practice are some that you also encounter with other technologies, and some which are very unique to quantum technologies. And one thing that's super unique is the accessibility of the subject. So we always quote Feynman when we start off presentations here, is that we say that he said, I think I can safely say that nobody understands quantum mechanics. Of course, we can put this in a mathematical framework and we can work with this, but quantum mechanics is something that's super counterintuitive for a lot of people, and they find a hard go-to to work with this, especially if they come from a practical application side. For example, think about automotive things, then the bridge to quantum mechanic world is super hard. Which comes to the next point, which means that we have a high requirement for the employees. That means that beyond their technical expertise, they really, really need to have skills in communicating, or skills in boiling down topics for other people, which come from a completely different expertise field. The next 2 points that are that we have as challenges in practice is that we have a fuzzy practical benefit. What this means, and this is different to innovative technologies like artificial intelligence, that on the one side, you have theoretical benefits, which are provably sound in mathematical frameworks, but transferring them into practical benefits is a completely different story. And a lot of those quantum advantage proofs get lost along this way of integrating this into a practical either business concept, or to say that the benefits don't lead to practical monetary gains. On the other hand, of course, because of this too, it's hard to assess when to start. So when is a good part where you say that the quantum hardware is as far emerged and evolved that you can say now an integration into the company makes sense. So of course you want those practical quantum advantages, but you want to know when is the right time to start. From this onwards, you also have the problem of expectation management. So we have a very, very huge hype. A lot of people think quantum tech is super cool. There's a lot of news there, which is of course great. And there's a lot of money out there. But the more you promise to people, the harder it also is to keep those promises. And if you promise too much and the things will not turn out to be there in the time frame that people expect, a lot of people are super negative about this technology and will be more on the side of, well, we heard about this 10 years ago already, then you didn't fulfill your promises. Why should we try this again now? So one has to be careful. The other thing is there's a different modi operandi, we call, from the different partners in this network. So we have a lot of academia-focused research groups, and on the other side, the industry, which have different values, different time constraints, and which of course also want different things. And putting those two together can be hard. So from our side, the main challenge is when and how to start as an automotive manufacturer. And for the when question, we did a lot of literature research when starting out. We talked with a lot of experts, and this is what we came up with, that we said we distinguish quantum tech in 3 fields: quantum computing, communication, and quantum sensing. And for all of them, we have different time frames and we have different approaches, which means that for the quantum computing, which is a lot of research that still needs to be done, we have a longer time frame than for quantum communication, where we say, okay, here we can already identify use cases or look at companies who actually offer implementations, which leads to quantum sensing, where we have a lot of companies which already can build sensors, might not be at the point where we can say, okay, they can build mass production sensors, which we need to have in the car, but maybe in a smaller number for certain test benches or stuff like this. The next question of how, we created an Ansatz, which is kind of on the direction of an agile manifesto, where we say, okay, this is taken from the agile software development, and we kind of put this into the quantum tech side and took what we need from this agile manifesto. So our Ansatz has 4 main points, where we say 3 main points, because the second one is kind of integrated already. And the number 1 point would be individual and interactions more than processes and tools. This means that we have a very small interdisciplinary team, where we have 1 seed employee with a PhD project in quantum computing and an automotive expert working in a tandem super closely, and they interact with the corporate and with the university side, which is also very close, which means we have it live in the real world, people being at a blackboard together and discussing together. The second point is functioning software more than comprehensive documentation, because right now we're not producing software for a mass market, but it's more like POC and trying out things. This is something that's integrated anyways. And it will more be the challenge to get out of this into something that has as much documentation that you can integrate this into an automotive process. The third point is that it's cooperation with the customer more than contract negotiation. The customer for us as a digital entity is the Porsche AG. So what we try to deliver to them are analysis which identify must, cans, and nots. This means what part of the technology do we really need, what is optional, and what also we don't need. And there's a lot of things out there which we don't need, and there's a lot of things out there which we really need, which is, I think, a really, really good statement for quantum tech in general. The fourth point is that we have responding to change more than following a plan. When we started off, we wanted to do quantum computing, but as we found out, this knowledge we have, and a lot of people came to us with quantum sensors and quantum communication things, for example, with PQC algorithms or quantum random number generators. And we tried to transfer the knowledge we have from quantum computing to those other fields. So here we really had to adapt quickly and kind of build or broaden our viewpoint on quantum technology in the moment of starting. So the key takeaways are there's a high risk for a company like Porsche to start too early and to communicate this wrongly and then burning the technology for those people. But there are great opportunities with a small research team and in this close cooperation with uni and with academia and industry of really fruitfully gathering new knowledge and delivering those results. Yes, and I have an example in the backup if you guys are interested, but you can also contact us for further questions. But since we have a few minutes, let me try to go into this. So one of the projects we have is called Hybrid. It's with Freie University Berlin, and it's sponsored by the Bundesministerium für Bildung und Forschung. And what is this about? This is a quantum classical hybrid algorithms for the automotive industry. This means that we take tools we have from the quantum world and try to see, can we get an advantage on one specific use case? The use case at the central viewpoint of this project is the job shop scheduling, which is known to be NP hard in certain cases. What we have is we have 1 postdoc, 1 shared PhD, and a master student working on all kinds of things in this area of this use case, which is at the centrum. This means we do, on the one hand, we develop methods in the field of quantum machine learning, for example, but also just in the field of showing quantum advantage proofs. We have the use case where we say we have a mathematical formulation of the job shop scheduling problem. We try to put code open source where we have first implementations. We seal prototypes, we seal patents, and we try to transfer that knowledge in the sense of letter of intents, or we have expert interviews with the Porsche AG and see what what does it need to come from this one use case into a real world application? So what would be the steps in the next 10 years to really integrate this technology and try to bring this knowledge back into the field, and especially into our academic partner to then see if we have to develop new methods, for example. Yeah, and you can get our publications online. So we do the usual path of academic research. And yeah, I think we're really, really happy with this modus and with this example project with the Freie University Berlin.
Thank you, Alicia. All right. Yes, please, if you have any questions, type it on the Q&A section, and Alicia will be super happy to engage in the discussion with you by the end of the event. Thank you, Alicia.
Yes, thank you very much.
All right, so now it's the time for Michael Brett. Hello, Michael.
Hey, great to see you.
Great. He's the worldwide business development and go-to-market strategy lead in quantum computing at the Amazon Web Services. So, are you calling from the US?
Yeah, exactly. I'm in Seattle this morning.
All right. Thank you for being here with us.
My pleasure. Thanks very much for hosting this event. And you know, we've got a modest crowd, but I think it'll be really great to interact with everybody and get to know everybody here and why you're interested in quantum computing. But thank you, Alyssa, for the great, setting the scene of like why companies are interested in quantum computing and some of the challenges that we've got in doing this appropriately. I thought that presentation was excellent in helping sort of set the stage for the motivation behind why some companies are exploring quantum. And I think I can complement that by adding the mechanism for people to get engaged in quantum. So my presentation today is to give a quick overview of what we're doing in delivering quantum technologies to our enterprise customers through AWS, and some of the investments that we've made over the last couple of years with quantum tech, and a couple of quick examples of what customers are doing in this space. So, of course, what is quantum computing? Well, it's a different kind of computer, not necessarily faster, but there's huge opportunity with a different form of compute that we might be able to work with. Give me one sec. Just need to turn off another thing. That's working. Sorry about this. I just had another call come in on a different technology. Share my screen. So it's a different kind of computer operating with a different kind of physics, and a different kind of physics means a different kind of math. Different kind of math means a different kind of algorithm. Different algorithm means we can solve problems in a different way. And so the way we think about quantum at AWS is that it's a different kind of computer. And it fits into our overall high-performance compute portfolio. So we have CPUs and GPUs and other specialty processors. Quantum computers are just one more tool in that toolbox to help our high-performance compute customers run their large industrial strength workloads over time. And so we're investing in quantum technologies through 5 pillars of activity. The first is the AWS Center for Quantum Computing. And so that's where we're building our own quantum computers. And I'll show you an example of that in a second. We've also got a research and development center that's exploring quantum networking. So everything to do with shifting quantum information around somehow, moving quantum information from one place to another. And so that includes quantum communications, quantum repeaters, quantum memory, connecting multiple quantum computers together. We're exploring that space. So we've got 2 research and development centers. We've also got a team called the Quantum Solutions Lab. This is the group that works directly with customers. So they engage on a long duration basis, usually 6 to 9 months. They'll explore a particular workload, exactly as Alyssa described, help those organizations get ready for quantum computing, become smart buyers of this technology in the future. We've also got a global network of partner companies that build on top of AWS. AWS is infrastructure. It's compute, storage, and databases. And companies build on top of that infrastructure to deliver to their particular clients. And so our partner network is huge. These are the small startup companies that are building on top of AWS. And they could be delivering solutions in the chemical industry, in the financial sector, in a whole range of different industries to, with their niche application built on top of AWS and our quantum computing solution. And then there's Amazon Bracket itself, and Bracket is the name of the service that we offer. It's a quantum compute service in the cloud. We make different forms of quantum compute available, and I'll show you a quick example of those in a second. So just want to give you a little bit more detail about the computer that we are building. So AWS is building its own quantum computer. We've got a facility based on campus at Caltech in California, in Pasadena. We've got a brand new facility there. It's kitted out to do research and development of quantum technologies. And we're building a superconducting-based computer. We're bringing along some technologies of our own around error correction and error mitigation. Hopefully we can contribute something to the overall superconducting effort. But we're in the early stages of building out our own system. And this is a long-term investment. It's not every day that even AWS builds a brand new research and development center at a university to explore a particular technology. So this is a long-term investment to focus on quantum computing and really understand all of the elements that are required to build up a supply chain, build up a manufacturing capability, build up a scaling capability. Quantum computing, when it becomes commercially advantageous, like when we get that breakthrough technology, that's the beginning of the journey for us. AWS is the service provider that will have to figure out how to scale this to thousands of computers in multiple data centers all over the world and running quantum compute at scale. And so we need to do the R&D to understand what it takes to build that supply chain, what it takes to scale that up. There's a lot more detail in the link that's on the screen right now about our particular computer and some of the milestones that we've hit along the way. So I encourage you to go take a look at that YouTube video. So the Center for Quantum Networking, we're building our own networks as well. So the movement of quantum information around. So this is a matching research center to the one in Pasadena, but the Center for Quantum Networking is based in Boston. It's attached to Harvard University. It's looking at everything from security to communications, post-quantum crypto, and quantum networks and repeaters. We've already deployed one quantum network already. There's a prototype test site with some partners in Singapore. So you can read about it on this blog, but a QKD-based approach to connecting multiple AWS data sites together and understanding some of the supply chain characteristics there. But this team is doing deep R&D into quantum memory and quantum repeaters so that we can connect multiple quantum computers together and hopefully computers across different data centers as well. So a long-term project in that space. So let's take a look now at Amazon Bracket. This is our quantum computing service in the cloud. We launched it about 3 years ago now. So we've been operating a quantum computing service, just like any other service from AWS. We've got CPUs and GPUs, and now quantum computers running in the cloud. This is a fully generally available service. It meets all of the requirements of being a generally available service of AWS. So that includes security and availability and support and documentation and all of the elements that make this a fully fledged service of compute in a global cloud service provider. So it's an environment to build, test, and run quantum computing algorithms. It's been built to allow you to explore quantum computing. Exploration really is the operative word here. This is an early stage technology. We need to learn about it and to try out different things. And so what we wanted to do was make available different technologies, a range of different computers, a range of different simulators, a range of different software libraries, so that you could try out different things and learn for yourself what quantum computing could mean to your organization. So taking a look now at the high-level architecture diagram of Bracket, Bracket is the orange box in the center there. It's part of the AWS cloud. So it's a fully integrated service of AWS, which means it connects into all of the other services. So everything from like security and user management, storage and databases, all of our machine learning tooling, all of our generative AI tooling, connects directly into Bracket. It's just an API within the overall AWS service. And that's an important differentiator for us compared to some of the other providers out there, is that it's not a standalone R&D environment. It is a fully integrated service as part of AWS. On the left-hand side, 3 different ways for you to access Bracket. We've got a ton of managed notebooks and examples and sample code that you can use, software development kit you can download and run locally, and then a GUI environment with a console that you can connect into Bracket. In the very center of the diagram are the simulators on Bracket. So these are emulators of quantum computers that run on our classical infrastructure. So running on CPUs and GPUs, but allows you to test out algorithms so that you can debug and do performance analysis before you deploy to the actual quantum hardware itself. Today on Bracket, we've got 4 different kinds of quantum hardware from 4 different providers. So ion traps from IonQ, superconducting qubits from Rigetti and Oxford Quantum Circuits, and Rydberg atom device from QEra. We want to provide users an environment where they can explore different modalities of compute. So try out the difference between ion traps and superconducting and compare the difference. Try out a different form of quantum computing with analog Hamiltonian simulation on the Rydberg atom machine. These are different ways of using quantum computers, and we'll be adding more to this lineup over time. We'll be adding our own hardware to this lineup when it's available, but also from other providers. What we expect is that as quantum computing develops and as hardware kind of goes through different testing cycles, and as we get different access to different machines, this lineup will change quite a lot over the years, and we'll be able to, users will rerun algorithms and try different things out with different platforms. If you've seen me present before, you might remember that there used to be a Xanadu machine on this slide and a D-Wave machine on these slides. Those have come and gone, and users have tried out different things, but we expect annealing and photonic devices to come back into this lineup over time as well. So we expect it to be quite a dynamic kind of marketplace for hardware. We'll be adding more hardware, certainly this year. But what we're hoping to see users do is to explore using this space and try out the different systems that are available when they're up and running. So simulators, we've got 4 different simulators. A local simulator you can run for free on your own laptop. You download that and run it as part of the software development kit. We've also got a state vector simulator, sort of the standard model simulator for quantum compute that runs on classical infrastructure. A tensor network simulator, which is really good for some quantum machine learning algorithms. And then a noise model simulator that allows you to look at the noisy characteristics of some of these early stage devices. These simulators allow you to run at really low cost. So for a couple of cents, you're able to test out your algorithm, run it up to the scale that we've got available on these, and make sure that you've got your algorithm right before you move to the actual quantum hardware itself. We've got a range of different quantum software libraries that we're adding on top of Bracket. So we talked about the hardware at the lower levels of the stack, and then at the top of the stack, we work with a range of open source providers, including PennyLane. PennyLane is our preferred quantum machine learning library. And so PennyLane is fully integrated into Bracket. It's part of the SDK. It's an open source library with a ton of examples of quantum machine learning tools. So you can look at Boltzmann machines and Born machines and different neural networks, and bring your existing machine learning libraries, so like PyTorch and TensorFlow, across to Bracket and then run it on a real quantum computer. You can also use KissKit with Bracket. There's a KissKit Provider, a KissKit Bracket Provider, so you can bring all of your existing KissKit code across to Bracket, connect into a Bracket backend, so IonQ or Rigetti or Oxford Quantum Circuits, using your existing KissKit library. And this is a great example of where AWS and IBM are collaborating in the open source community. We see this as an opportunity for us to build up a user base, together that knows how to use different libraries, different techniques in quantum computing, and have a selection of choice across different backend providers. So we're excited to co-develop this KissKit Bracket provider with the team there. So let's take a look at what some customers are doing on Bracket. The financial services industry is one of the most active sectors in quantum computing, and in general, they're looking at the applications around optimization problems, machine learning problems. So everything from like portfolio optimization, risk analytics, fraud detection, that kind of thing. Really early stage. These are explorative type projects, capturing intellectual property, doing workforce development activities, so that they can try different things. But we've got customers like JP Morgan that are looking across portfolio optimization type problems, characterizing performance, using advanced features on Bracket like hybrid jobs, both the quantum and the classical elements to that work, and publishing the work. We've also got customers like BMW that are looking at chemical simulation type problems. So problems like the oxygen reduction reaction problem, which is a key problem in novel battery design for electronic vehicles. The transition from a platinum cluster with a group of catalyzing that reaction from going from one state of the matter to another. That problem is a very computationally intensive problem for classical computers. We're able to take a look at that with quantum computers. And so we worked with the team at Quantinuum. They've got a package, a software package that sits on top of Bracket called Quanto. That package looks at chemical simulation type problems like this. Again, super early stage. These are small molecules, just a couple of atoms. But as these computers get bigger, and as we're able to fit bigger and bigger molecules onto these systems and look at bigger and bigger reactions, we'll be able to hopefully get a better understanding of what material science is doing, what the chemical industry needs, from everything from adhesives and abrasives and sealants and battery design and those sort of technologies, so that we can build more efficient systems in the future. But then our biggest group of users are the research customers that are using Bracket. So universities and research labs all over the world, organizations like NASA and the Department of Energy that are using Bracket as a research platform. So accessing different quantum computing technologies, running different experiments from physical sciences to computer sciences, looking at problems like the efficiency of running the Fourier transform implementation for a particular workload, and publishing those results using real infrastructure to get experimental results out of that and explore this space. So that's all from me. Check out the blog on the AWS website. That's where we publish all of the information about what our customers are up to, the latest on what we're doing with Bracket, what we're doing at all of our research centers. There's my email address. Feel free to reach out anytime. If you're a researcher, we've got credits programs that we can help offset the cost of your experiments on Bracket. If you're a startup company, we've got programs for startups across AWS as well. We can help you navigate that environment, and look forward to questions along the way.
Thank you, Michael. Thank you for sharing your future plans on Amazon Web Services and what you are doing for the industry. Yes, of course, for the viewers, if you have any questions, feel free to put it on the Q&A. I already saw some questions. Also, Alicia answered one of them. But anyways, we will have a engaging discussion, all of us, by the end of the event. So no problem. You can answer them in the end. Okay. So now it's the time for Adrian Vetter. He's head of software at PlanQC. As I mentioned before, they joined very recently QBN as a new member. So yeah, welcome, and the floor is yours.
Yeah, thanks a lot. Also, thanks for adding us to the business network. So let's get started. Yeah, I'm from Blank, and today we want to talk about the way to practical quantum advantage with neutral atoms. First, I will tell you a little bit about Blank, what it is, why we are giving this talk, basically. So Blank is the first startup that emerged from the Munich Quantum Valley. This is an initiative from the state of Bavaria in Germany. And they had a total funding of 600 million into quantum technologies. So the idea is to bring quantum technology into the real world. And 60 million out of this pot went into a neutral atom quantum computing. And the idea of this Munich Quantum Valley is to create a 400 qubit machine until 2027, 99.5 fidelity. And first startup out of that is Blank, and it was founded by Alex Gletzle, Sebastian Blatt, and Johannes Zeyer. And they all have a strong background in quantum information and quantum physics. And Sebastian and Johannes are still at the Max Planck Institute for Quantum Optics. And this is why we already built on a decade of knowledge, or multiple decades, more or less. So we don't start at zero. And this also convinced some investors. So at the right side, Speed Invest, we see Amadeus, Apex Ventures, and they spent a little bit more than 6 million euros on us as initial seed round. And Markus Wagner and Christian Achleitner and Hermann Hauser. Like Hermann Hauser, he invented the ARM company, or was founder of the ARM company. Yeah, all board members. And this business background and also some backup from the scientific side. So also from the Max Planck Institute here in Munich, Manuel Bloch and Ignacio Serac from the experimental side and the theoretical side. They support us very good. And for quantum algorithms, there's Dika Yash from Hamburg and Oxford, and Markus Müller, an expert in error correction. With this background, 1 year ago, we were founded. And until now, we are around 16 employees, probably a little bit more now. And also rented a quite large office and laboratory space in Munich. It's 1,400 square meters, it's quite big, it's an old hardware store, and we are renovating it quite now to build up our own machine there. So what are we really doing? So the idea is to commercialize neutral atom quantum technologies. So you want to build a commercially usable quantum computer. And we don't want to just build this computer, but we want to build the whole stack. So we have the end user in mind, and we create also the software you need and algorithms. And if you need consultancy, then we can also provide this tailored to the neutral atom platform. So the back here on this image, you can see a lab prototype that we have. So the right top, this is just a laser pointing at a camera, but the important part is here in the little bit in the middle. Like this is our vacuum chamber, and there we have strontium atoms. And can you zoom in a little bit? This looks like this. So this is a vacuum chamber, and in the middle here, the
yeah. Hey guys, sorry to be late. I was just doing an event.
Are there any questions? If not, here what you can see is a cloud of strontium atoms, and this is in a vacuum chamber, a glass vacuum chamber. And at the bottom, you see a microscope. And if you look through this microscope at these atoms, this looks like this. So these atoms, you can see, are these red dots. It's the big red dots. The small one is noise. So these are individual atoms. They are super cold, like they are probably one of the coldest things in the universe. It's colder than in outer space. And we can trap them in space. And you can see here a 4x4 rectangular lattice. And this you can do computation. And how this works, I can show you briefly. So basically what we do is we store quantum information in a single atom. So each of these atoms are the same. So we don't have to manufacture them. So they are just there, basically. So they are the same on Mars, they are the same on Earth. And when we have one of these trapped, we can encode the quantum information in the outer shell. So these are like this, the core, and these are electrons. And the qubit can then be encoded here. Basically, in this example, we encode it in if the electron has been to the right or to the left side. And you can then manipulate this with lasers and do calculations on it. There's another feature of these neutral atoms. It's called the Rydberg state. And when you now take the outermost electron and put a specific amount of energy with a laser on it, then you basically throw it away really far outward. And this is called the Rydberg state. And to give you a number how far this is out, if the core would be a baseball, the electron would be 130 meters away. So it's really, really far. This has two other properties which are very good or very in advantage to build a quantum computer. It has a very long lifetime. It scales by exponent of 3. So you can do calculations without losing your state. And you have strong interactions. So it's the power of 11. So it's really, really strong. And this you can use to create a so-called Rydberg blockade. So let's have a look at a grid again. It's basically the thing we saw from a microscope. Qubit or an atom. And now this one got excited to the Rydberg state. So the electron is kind of here, circling around. And it blockades these atoms to going also in the Rydberg state. So the energy is so strong, you cannot excite two of them at the same time. And this is a feature you can exploit to create entanglements. This is one of the bases of quantum computing. So this is the core technology which is used in neutral atoms. So now to put into play quantum advantage. So quantum supremacy, most of you probably know. Quantum advantage, probably most of you, but just to give this one overview. Quantum supremacy is demonstrating a specific quantum computation that is infeasible for classical computers. Google showed this 2019 in the Supremacy experiment. They used 53 qubits. There were examples how to do it much more efficient on classical computers, but nevertheless, this was the beginning. Then there's quantum advantage, which is achieving a computational advantage in real-world applications. Like the most known is probably cryptography, like Shor's algorithm. Then material science is very promising, like the pharma case, which is also the next talk. Battery science, well, we already heard something before, and also chemistry, like everything in material science looks very promising until now, but you need hundreds to thousands of qubits for this. So what is Planck doing on this way to achieve quantum advantage? So for now, we just have a quantum simulator, but we are now already building a quantum machine. So we got so the German aerospace agency bought a quantum computer from us, and this one we are building. We're also building our own too, and we aim to have so around 2024 one with 1,000 atoms. It's not 1,000 qubits. It's just that we can trap 1,000 atoms, And then we have 20 qubits, 99 fidelity. And 2 years later, we aim for 400 qubits. It's basically the same aim as the Munich Quantum Rally has. It's 99.5 fidelity. And then fault-tolerant quantum computing. So this is also why you need, like, we aim for 99.5 fidelity. What we think is that quantum advantage can only be reached with fault-tolerant quantum computing. So probably we have to wait a little bit until this is possible, but it's not that far out, so it's still into reach. And there are some challenges on the way, at least for neutral atoms. And neutral atoms is a very new platform. There are also some other companies out there, they work on this, but it's still compared to superconducting, very new. We still have to reduce a lot of noise sources because our atoms are very noise sensitive. This will also improve the qubit fidelity. So this is really important to have very good qubit fidelity. Or the results are not good enough. Then quantum error correction is important. And advantages of neutral atoms is basically that all qubits are identical. You don't have this complicated manufacturing process. So we just get some strontium, and that's basically our qubit. It's highly scalable. You saw we can place individual atoms, and if we trap 10, 100 or 1000, it does not matter that much. It's quite easy to scale up in this direction. Everything works at room temperature, so we don't need any cryogenics. So it should be easy to run this in a high computing center. So that's also our goal, to sell it to high computing centers. And the atoms have very long coherence times, so deeper circuits would be no problem. So that's from my side. Thanks everybody for listening. We will be also at a World of Quantum next week, so feel free to drop by. And if you have any questions, feel free to contact me. There's also my email address, or come by at the World of Quantum. I would be happy to chat with you. Thanks a lot.
Thank you, Adrian. Thank you so much for sharing what's behind your research and also sharing the roadmap of Plan QC. And yeah, thank you for your time. I see you on the World of Quantum.
Yeah, thanks a lot.
And last but not least, we have with us our top speaker, Nikolai Maul. He's quantum computing scientist at Beringer Ingelheim. Sorry if I don't say it in the German accent. You will say it much better than me. So thank you so much, Nikolai, for being here with us. And I can't wait you to be on the stage. So the floor is yours.
Thank you very much for having me, and thank you all the previous speakers for the interesting talks. And so I'm going to change gears a little bit. I'm going more into the software side, and so I'm going to talk about what we can do with quantum computing in drug design. So we're a big pharmaceutical company. I'll just give a small overview. So we still are completely privately owned by a family, and quite old, over 100 years old. And the focus is on human pharma, animal health, biopharmaceutical, contract manufacturing. And we have around 50,000 employees worldwide. And as all pharmaceutical companies, the R&D expenses are quite high. So if we spend around 5 billion a year of our revenue of 25 billion. So in pharmaceutical, there's a drive always to have the new drugs, the new therapy, and so on. And we were the first pharmaceutical company to partner with Google Quantum AI. So, oops, why is it not going forward? Okay, so who are we? So we're a team of 4 quantum computing scientists right now, so we're probably one of the biggest teams in Germany, and we're all mostly from the quantum computing background. So Matthias de Grote, he did quantum chemistry and quantum computing. I'm also from the quantum chemistry side. Michael Streif is more from the machine learning side, and Rafael Santagati too. And our boss is Clemens Uchikocik, who is the CTO of Boehringer Ingelheim. And then we have our close partner, who is the head of CompChem. So we're mostly working with him right now. And he gives us the business use cases inside the company. And how do we work? We collaborate inside and outside with teams, so with startups, so in big companies like Google, and inside to try to find the use cases. And we also try to drive these use cases beyond of proof of concept a little bit, which is a little bit challenging without having a quantum computer. So you can only estimate how things will run, but that's what we're trying. And we're trying to really develop new algorithms and drive the research in the right direction, and also the community to a little bit show what we need. If we would have a quantum computer, what we need from the software side to really use it also in drug design at the end. So how is a drug discovered? So first you discover I just have to move this thingy here. Okay, the target. So it's mostly a protein in the body, which you want to inhibit. And it's a protein where you can bind some small molecule inside, and this will inhibit the function. And this is what people find first. And then you try to find some molecule which inhibits it first. And this molecule is out of one molecule out of 10 to the power 60 molecules. And there you see the combination is really, really huge of the types of molecules you can try. And then you try to get a better molecule and go down from 10,000 molecules to 200 molecules. And then after 6 years, you will have the drug candidate, and you have around 5 molecules. At the end, you will register one molecule, which is around 10 years of drug development. So it's a very, very long process. And people are using right now also computational methods like molecular dynamics or quantum mechanics, but it's still used not that much as in other industries, because there are no reliable quantum chemistry methods. And this, in principle, could be solved by a quantum computer. So we really need predictive calculations of chemical properties, and the quantum computer could provide this if we would have one. And one of the first molecules we calculated, before I go there, just to show you where these quantum chemistry calculations are in this development process of a drug, is they're pretty much at the beginning of the research. So molecular dynamics with binding affinity predictions are really at the start, where you try to figure out different types of small drug molecules. Then later on, if you have some molecules, you would do ADME predictions, which means it's absorption, excretion, metabolism, and excretion. So you want to find out if something is toxic, if it can be absorbed, if it can be distributed through the body, if it can be also broken up by the body and also excreted by the body. And then at the end, you also have preclinical development, clinical development. In principle, a quantum computer could help there too, but these are more like machine learning tasks, and we think that this is a little later than quantum chemistry. So we're right now focusing really on the two situations in the beginning, which most can benefit of a quantum computer. So what are good pharmaceutical use cases in the research phase? So in the really early phase. So most drug molecules are really well described with approximate methods right now already. So if you use DFT or so, you can calculate quite good. But there are a few examples which are potentially hard systems, like proteins with metals, like P450. So this is a protein which has an iron in the middle. And are there other hard and relevant systems of pharma in the world, and how many? And maybe the alternative would be to have also approximate methods on a quantum computer, which could be much faster. And then the question is, what do we want to calculate in drug discovery? And in principle, a single point energy calculation is not really interesting. You need computations of millions of configurations because the protein can be in different geometrical configurations, and also the ligand, the drug molecule. And you have to calculate all these different possibilities because you have to calculate the entropy terms also, because you have finite temperature, room temperature of the body normally, or body temperature. And then this makes it very difficult. So you have a huge amount of calculations. Can a quantum computer help there? And then you want to go and calculate observables, properties of your molecules beyond ground states, forces, excitedness. And molecules are normally not in isolation, not in vacuum, but solvent effects must be included also. And this leads to even more configurations because all the single water molecules can be in different combinations. And this shows you also why quantum chemistry is such a tough cookie to break. And that's why it's not applied as much as in other industries. So one computational cost we calculated for one relevant system, and this system is the cytochrome P450, which I already mentioned. It's a heme protein. It's a huge protein which has a couple of thousand of atoms, and inside there is this heme group, which is shown here, and we calculated only a small part of the heme group, which is shown here. And it's a carbon network with nitrogens. The blue one is nitrogens with the iron atom in the middle, and that it does most of the catalysis. There are other metals also in the body which do also catalysis, but it does the oxygen catalysis in the body, splitting molecular oxygen to atomic oxygen, and also does a lot of the metabolism of drugs. So it's a very important. And we try to estimate how long it takes with a quantum computer, if we would have a quantum computer now, to calculate the ground state energy, so one number. And it's a very expensive algorithm, the quantum phase estimation. It needs many quantum gate operations. So you cannot do it without error correction. So it's known as a problem. And so the system size is around 500 orbitals, and we only have this very small part of this big protein. So we cut a lot away, but we still have 500 orbitals. But from these 500 orbitals, we selected then only 60 orbitals, which are the important ones. And this leads us to 1,400 logical qubits, which means if we take the error correction schemes, which we want to have nowadays, to 4 million physical qubits, and around 8 billion gates, which would need to runtime of 3 days. And then we would have one number. But they're quite big numbers, but they're not, in principle, telling us that we don't have to go forward, because I think these numbers will come down, but eventually, but we have to work that they come down, because we need thousands of these calculations, and we cannot wait. If we have 1,000 of these calculations, we cannot wait a month, because in principle, a drug can be synthesized and tested in 2 weeks. So if a chemist says we need this kind of drug, we can test it around in 2 weeks. So we have to beat the experiment, and so runtimes should be in that order at the end. And then I just want to shortly talk about some other quantity which we are very interested in. That's the binding affinity of a drug. So here shown are different configurations of a drug molecule, and just one drug molecule can fit into this protein pocket as shown here, and has the right energy. And this energy you want to calculate. And normally you can calculate this interaction energy just by calculating the total system, so the protein with the drug inside, that would be AB, and then you subtract the total energy of the one system A, the drug, and subtract the total energy of the protein, and this would give you the interaction energies. You have then some technical problems, but the biggest problem is that these numbers are quite big, the single numbers, but this difference is very small. So you can see it's around 1,000 or even more k-couplable, and the difference. And this leads to the fact that you have to make these calculations quite accurate to get the right numbers. Note that the free energy contributions are not included here in this scheme, which have to be included to get right numbers at the end. And so we were looking into how to do this on a quantum computer. And there is this symmetry adapted perturbation theory, which people use on the classical machines, but you can translate this on the quantum computers. And we've shown this for a NISQ machine and also did this for a fault-tolerant machine. So here you, have, for example, have the interaction of two benzynes, and you calculate the 1 and 2 RDMs, so the density matrices, and then you can get the induction, dispersion, electrostatics, and exchange of the coupled system. And here you can see some numbers of the benzene, where you see, in principle, the dispersion energy and the exchange energy, they dominate most of the total energies. And then we looked how to implement this on a fault-tolerant machine, so with error correction. In principle, this is a very abstract the algorithm which you would have to implement. And what you have, in principle, you have to do a QPE. So it's where you have these controlled unitaries. So the unitary is the unitary of the observable you want to measure, and you have to do the single one, the squared, to the power of 4 and to the power of 8. And inside of these unitaries, there is another QPE. And this means you have these nested QPEs, which makes it very expensive because you have to create the quantum state, which cannot be copied again and again. And this leads then, if you want to calculate such a symmetry adaptive perturbation theory on a fault-tolerant quantum computer, that you need around 6,300 logical qubits, 17 million physical qubits, and a lot more gates. So we'll really have to look if we can find faster algorithms than QPE or speed it up in a certain way, that we can do more than just ground state calculations. And with this, I would like to conclude. Really, classical algorithms have too many approximations to be predictive. Today's quantum algorithms on quantum computers are only advantageous for a few hard systems. So the P450 is a system, for example, where a classical computer cannot solve. And so really to generate quantum advantage in the pharmaceutical industry, we need to really improve the existing quantum algorithms for energy calculations, also develop quantum algorithms for novel applications, so beyond energy. And really we need hardware. Then we can test the algorithms and then also make heuristics. Also on classical computers, everything is based on heuristic algorithms, and your systems are not always as hard as you think, and you can do a lot of shortcuts and make the algorithms faster. So really, there's still years of basic research required. And if we would have a quantum computer today, we wouldn't use it because it would be too slow, the algorithms. So we really have to work on the algorithm side. And with this, I would like to conclude, and thank you very much for your attention.
Thank you very much, Nikolai. Super interesting, because I am a pharmacist, so I was enjoying a lot your pitch. And so thank you so much, everyone. Now is the time for the Q&A section. I saw that you guys asked some questions, and our speakers have already answered them, but let's discuss all together, because that was the main idea of the session, and I think it's more fruitful if we can interact and engage with each other.
Maybe I can answer the question about the IBM 100 times 100 challenge. So
Please.
I mean, they have this Nature paper out since last week, I think, where they the Ising model, where they put together 2 error correction schemes. This and I think this is very good, and I think it will help probably to reduce the number of qubits you need in error correction at the end. If you look at these things, that maybe you can do some approximative calculations before you have a really full fault-tolerant machine, but it's not clear yet. But I think it's a great step forward in that direction. But certainly, I mean, you could see for quantum chemistry is a very tough cookie. I mean, it's you need very highly precise numbers. So I think without a lot of correction of errors, it's not possible to do these calculations.
All right. Thank you, Nikolai. Any words? Oh, maybe Jan wants to say the last words or comment on Nikolai's answer. If not, we can comment the other questions. Okay. So Gerd Grammel is asking to Alicia, when do you expect to productize a quantum-enabled product or service? If you want to add some words on your answer, Alicia, maybe?
I think we have to differentiate. So we have some quantum sensing applications already in internal services for example, measuring magnetic fields already now. And we expect quantum communication and computing to, take on a little bit later. But we have quantum-inspired solutions already now where we say, okay, we do the detour about finding a good quantum algorithm. We learned so much about our problem at hand. And with that, we can find a better classical solution right now. Yes, so I think a bit of patience and waiting for the computing part.
Mm-hmm.
Maybe a follow-up question on this, Alicia. But first of all, thank you very much for your super exciting and insightful talk. Is there a clear expectation from the management? So a clear roadmap for Porsche when you expect really to have a business impact or a quantum advantage, a practical quantum advantage? Or are you able to just play around at the moment and see when you can come up with something practical?
Yes, so I think measuring when like an innovation entity actually gets results is super hard, and I think it's one of the key problems to have those measurable results. But what we do have is patents, for example, which bridge the time, and we don't have a clear time where we say until then we have to have those and those results. That would be a bit like looking into a crystal ball, which is not something we really want to do. So we try to find impacts which we have now already and try to foster them along the line.
That's great, thank you.
Good. Thank you, Johannes. I saw Michael maybe wanted to say something. I saw your microphone was.
Yeah, I was just jumping in on a question that was asked in the chat about how does AWS address the field of quantum communication. So there's 2 answers to that. It depends whether we're talking about post-quantum crypto and the measures that have been standardized by NIST in the US and other agencies to look at how do we protect against a future quantum computing threat and the measures that we need to implement today. So AWS is rolling out all of the recommended standards for post-quantum crypto to our existing services. So if you're an AWS customer and you use any of the communication services of AWS today, the post-quantum crypto standards will be added to that as sort of a free enablement. Like it's just part of the infrastructure. There's no additional work to be done. It's just like we're adding those mechanisms to the existing tools. So that's for the post-quantum crypto standards. The quantum communications itself, like how do we use quantum information to secure communications in some way? You know, that's the work of the team at the AWS Center for Quantum Networking in Boston, and it's early days for that. You know, the building of quantum memory and quantum repeaters, connecting multiple quantum computers together. You know, it's still a R&D activity. You know, potentially using quantum information as a form of security itself, you know, whether that's QKD or something more elaborate, you know, that's still an early stage technology. It's not something that we're planning to implement anytime soon, but we're certainly investing in the R&D of that space. So it's very much a research, you know, effort for us at the moment. One thing that we will be looking at doing is, you know, working with partners that build those technologies. So you know, the likes of a QSecure or you know, ID Quantique and so on, you know, how do they connect into AWS infrastructure for your customer?
All right.
I would jump in there because I also have a follow-up question for you, Michael. So you already mentioned the partnerships, and yeah, I think you already have great and unique collaboration partners for your platform, for example, like the QBN members, Pascal, Contino, and Rigetti, and so on. So what is the next step for you, especially as a business developer, and what you're looking for in terms of partnerships, support, collaboration in general?
Yeah, so the main thing we're looking for are really advanced use cases for the infrastructure that we've got. You know, we've got a really good handle now on sort of doing quantum education and, you know, helping people like get introduced to quantum computing and, you know, run their first quantum computing circuit, you know, try things out for the first time. So we're good at that, and, you know, there'll be an expanding market for that over time. But what we need are exactly like our friends at Boehringer Ingelheim just described, like there's really advanced use cases, the problems that are going to push the boundaries of what we've got available today, whether it's on the classical side or the quantum side, you know, what's going to drive our requirements for the future. You know, one of the lines that we use all the time is that the primary purpose of Bracket today is to learn how to build a better Bracket tomorrow. You know, we know that, you know, quantum computing is a future technology, but it's the use cases that will drive our requirements. So everything from, you know, what libraries do we make available? You know, do we need things like pulse level control and parametric compilation? You know, how advanced do those features need to be? How do we architect it? Like, how much is latency a factor? How much is the provisioning of GPUs on-prem alongside quantum computers a factor? You know, how much does compilation come into the overall strategy? You know, all of these sort of open questions about scale, you know, are what we need to answer, and so we need the advanced use cases to drive, you know, our understanding of the customer need. So the customer need today is from research customers and from enterprise companies like Porsche or Boehringer doing advanced use cases, and so we're looking for more examples like that we can work with partners on.
Good to know that we are all well connected. So there is another question from Jan. I don't know, Nikolai, if you are able to see it. If not, we can comment it.
I have to unmute myself, sorry. Yes. So the question is, yes, for the times, the estimates, he would like to know how fast the gates are. And I think it was around, I'm not sure, around like a couple hundreds of nanoseconds gates. So it's faster than what you can do nowadays, but I think it's not out of the realm how fast you can make the gates. And if you maybe you could make them even faster. It always depends a little bit on the interactions between the qubits. If you can strongly interact the qubits and turn this interaction off completely again. And this is a tricky thing. In superconducting qubits, you have this electromagnetic waves which go over the whole chip. If you couple them too strong, you get this a crosstalk everywhere, and you would like to avoid it. But I think people are looking at that and improving it every day. And I think until we have a fault tolerant machine, gates will be faster in all types of computing, probably.
Good. Thank you so much. We still have a couple minutes for the last question, if anyone wants to jump in.
Yeah, I have a question for Adrian. So maybe it's a very frequent question for you, but not less interesting, I think. So when can we expect your computer in the cloud? So hopefully before you achieve the practical quantum advantage, right?
Yeah, that's a good question. So building a quantum computer is not easy. So it will take a couple of years, but we are already looking at all the frameworks out there, also AWS Bracket for sure. Yeah, we can integrate. Also, probably the first customer will be high computing centers. So they will integrate it first, because when they just buy one, they have priority access, and then they give their customers first access to it. And there are some on the line who want to buy one. And so I would get like in 5 to 10 years, there will for sure a blank machine accessible from the internet.
Sounds good. And before I have to buy one for myself, if
Yes.
I want to have some.
Just you.
Okay, great.
Hopefully you'll get to try it on Bracket first before you have to buy one.
That would be maybe the fastest way, yeah. Sounds great. Adri, do you have any other questions from the Q&A box?
We don't.
Okay, maybe I have one question for everyone then, as a final one. So what would be, maybe in 1 or 2 sentences, your recommendation for all the quantum enthusiasts out there on how to step into quantum and how to become a leader as developer or end user of quantum?
Maybe I'll start. I think there are a lot of, like AWS and IBM, and they have very good tutorials, also Google. And I think taking one of these and just starting, you can learn a lot by just doing it, playing around. And I think that's the first step you have to do, because it's a little bit different, the quantum world. So you have to experience it, I think.
Yeah, definitely is.
Yep, completely agree. It's about experience and getting hands-on and trying stuff out for real. Once you kind of get through the initial, here's how to learn about quantum computing, I suggest everyone take a look at the Unitary Fund. The Unitary Fund is a open source, not-for-profit fund that sets essentially challenges for quantum computing in the open source community. So they have like micro grants available. You can get paid to do like a little bit of quantum computing work. A couple of $100 to take on a particular challenge. It's a really great resource to kind of be part of the open source community, take on some challenging problems, and potentially earn a little bit of cash on the side as well.
Yeah, great recommendation. Adrian, what's your one?
Yeah, also some friends out there like the IBM challenge. I think this motivates a lot to just participate in one of these challenges. There are also some universities who have challenges, and there's free tutorials out there. So if you're interested, if you're curious, going practical is, I agree with Michael and Nikolai. It's the best way to go into it.
I would add on this and say that once you did all this, you should try to find an expert which you can work with very closely, be it from a computing company or a research institute, where you say with them together, you can really get your affairs on the streets.
Yeah, that's a really, really good recommendations. Or join one of the great companies that are already out there. It's also a good idea.
Come work for AWS, exactly.
Yeah, then thank you so much from my side. Adri, do you have any final words? Yes.
Thank you, everyone, the attendees, the quantum enthusiasts, the speakers. We are super happy to have you here with us. From different industries, using and working on quantum technologies. It's super interesting. So that's all from my side. Thank you again for your time, for your experiences, for being here with us, and that's all. See you next time. See you for those that are going to be World of Quantum. See you there. For those online, we are going to see each other very soon for the next Quantum Leadership Session. We're going to keep doing this because we think that the industry needs it to make a strong quantum industry all together. And yeah, just keep in mind that we are organizing this big conference in business and technologies and industrial applications in Stuttgart on the 10th and 11th of October. So we wait for you there because it's going to be a big conference. And also we invite you to reach out if you want to become a speaker and boost your visibility. So that's all from my side. Thank you so much, and see you on LinkedIn, I guess.